Today, we're going to talk about a pillar of modern physics, the Higgs field. For years, we've been told it's the reason anything has mass. But what if that whole story has a fundamental flaw?
You've definitely heard the story, right? The Higgs field is what gives everything mass. But what if it's not really an answer at all? What if it's more of a placeholder, a stand-in for a physical mechanism we just haven't understood yet? That's the big question we're digging into.
Okay, so before we can jump into a new idea, we really have to understand the old one. So let's start with how the standard model sees the problem of mass.
Now, the story they teach you in school is pretty simple. The entire universe is filled with this invisible energy field, the Higgs field. And as particles move through it, they kind of get dragged down, and this drag is what we feel as mass. Sounds pretty elegant, right?
Well, here's the thing. The Higgs field didn't start its life as a physical theory. It started as a mathematical necessity. A patch, really. Without it, the equations that describe some of our fundamental forces would just break. They'd spit out nonsensical, infinite answers. So the key takeaway is that the Higgs was added to make the math work, not because we observed a physical process for how mass is made.
And this brings us to the biggest hole in the entire story. The Higgs mechanism doesn't actually predict the mass of a single particle. It can describe the how, but it can't tell you why an electron has its specific mass, or why a top quark is hundreds of thousands of times heavier. The all-important why is just completely missing.
And when you look a little closer at how the model actually handles those specific masses, you find something that feels less like a fundamental law of nature and a lot more like a bug in the code.
So how does the standard model assign these masses? Well, it uses a set of special, custom numbers. For all the particles that make up matter, electrons, quarks, what physicists call fermions, it needs at least 13 of these numbers just to get started. These are called Yukawa couplings, and this is the bug. They aren't derived from some deeper principle. There's no formula for them. They are literally just numbers that physicists go out, measure in an experiment, and then plug into the equations by hand, so the theory matches reality. The theory doesn't predict them, it just has these empty slots you have to fill.
This quote from the source material just perfectly captures the feeling. It really does feel less like a profound discovery and more like an ad hoc fix. A patch that was designed to make a broken calculation work, not a true explanation of how nature operates.
And this isn't just a problem with mass. When you zoom out, the entire standard model runs on over 26 of these unexplained free parameters. These are fundamental constants we have to measure and plug in, with no explanation for their values. It's a theory that's amazing at predicting things, for sure, but it's not very good at explaining them.
So, if the Higgs is a mathematical patch, what's the alternative? Let's explore a totally different model that rethinks the very foundation of physics. It's called the harmonic scalar framework, or HSF for short.
Okay, so instead of this whole zoo of different particles and fields, HSF says that everything, and I mean everything, is just a manifestation of waves. In this picture, particles aren't little dots. They're stable standing wave patterns, like when you pluck a guitar string and it vibrates to create a perfect, clear note. And fields? Those are just the waves moving through space.
Now, what's so cool about this is the shift in thinking. HSF throws out abstract just because fields, like the Higgs, and replaces them with something physical, real waves with real geometry carrying real energy. It's trying to build a mechanical model of how reality works, not just a mathematical description. And with this totally new foundation, we get a completely new and, frankly, much more direct explanation for what mass actually is.
In this wave-based universe, HSF suggests that every particle has a specific channel just for storing energy, almost like a personal battery. This channel is called K4, or the neutral field. And according to HSF, a particle's mass is simply the total energy that's been stored in its K4 depot. So mass isn't an interaction with some external field. It's an internal property of the particle itself.
So how does this work in practice? Well, you can think of it as a simple energy routing process. First, energy is injected into the system. Second, a stable wave pattern locks into place. This pattern is what defines the particle's identity, its spin, its charge, the whole shebang. Third, the total rest energy of that pattern gets deposited right into its K4 battery. And that stored energy is its mass. Finally, if the particle ever changes state, any extra energy just overflows and gets released as other particles, like photons.
Of course, this raises a really obvious question. If it's all just stored energy, then why does an electron store so little, while a top quark stores a ridiculous amount?
And this is where the elegance of the model really comes through.
Different particles are fundamentally different wave patterns. They have different geometries, different structures. A simple pattern, like an electron, has a small K4 depot. It just can't store much energy. But a much more complex, intricate resonant pattern has a huge capacity to store energy, and so it has a much larger mass. The mass is derived directly from the particle's structure, not from some arbitrary number you have to plug into an equation.
So, we're left with two very different ways of looking at our universe. One is based on a mathematical fix, and the other is based on physical geometry. Let's put them side by side to really see why this alternative is so important.
At a high level, the difference is just stark. On one side, you've got the Higgs model, where mass comes from an abstract mathematical field and needs a bunch of arbitrary numbers to work. On the other side, HSF says mass is just stored wave energy, and its value is derived directly from the geometry of the wave pattern itself.
Now let's look at the most important part of this whole comparison: testability. The Standard Model's big win was, of course, finding the Higgs boson. But HSF isn't just a nice idea. It makes its own concrete, testable predictions. It suggests that if we look really closely at things like the magnetic wobble of a particle called a muon or the frequencies of neutrinos, we should see tiny differences from what the Standard Model predicts. It even suggests we might find new flashes of light, these spectral lines, from K4 energy overflows. These are things we can actually go out and look for.
And this is the most crucial point. An alternative theory is only useful if you can actually test it. HSF gives us a clear path to do exactly that. By looking for these specific experimental signals, we can actually try to figure out which picture of reality, the mathematical patch or the physical resonance, is closer to the truth.
So we're left with this question. Is mass the result of a drag effect from an abstract, universe-filling field that was invented just to fix an equation? Or is it something more tangible? The stored energy of a physical, resonant wave that defines the very existence of a particle? The answer's out there, waiting for us in the data.